In this lesson, we're going to talk about the properties of real numbers. In math, properties are statements that are true for any numbers. They justify steps when simplifying expressions and solving equations. Let's look at the first property here. The first property we're going to talk about is the commutative property. The commutative property works under addition and multiplication. So the main idea behind the commutative property is that the order of values does not matter. What I mean by that is, I can have an expression like A plus B, and I can also flip those two letters around and have B plus A. And either way that I have those letters, the answer will be exactly the same. Let me show you what it means in numbers. So if I have something like 2 plus 3, I can also say 3 plus 2, and I will end up with the same answer of 5. I can also use different variables like x and y, so I could say x plus y equals y plus x. And I can also have examples with multiple numbers or variables like 3 plus 2 plus 8 and 8 plus 3 plus 2. Notice that I changed the order of the numbers, but no matter what, 3 plus 2 plus 8 still equals the same thing. Now this also works for multiplication too. So you can take all of these examples and change them to multiplication and it works the same. For example, if I said A times B, it's also going to be the same as B times A. I can also say 2 times 3, and that would equal 3 times 2. Now, and I can do that all the way down for all of these examples. So basically, a great way to remember the commutative property is if you see commutative begins with CO. CO. And I like to say that that means change the order. So if you change the order, it's okay that the answer will still remain the same. The next property we're going to talk about is the associative property. This property is seen under addition and multiplication as well, just like the commutative property. And the main idea is that groupings of values does not matter. So I'm going to put groupings here. And what that means is, let me show you here with some variables. So if I had A plus B, and then I added C to that quantity, that whole thing would also be equal to A plus B plus C, where if you notice that my quantities changed. So over here in this grouping, I have A plus B, and over here in this grouping, I have B plus C. But no matter what, no matter if the groupings change, please notice that the order does not matter. I have A, B, C on the left, and I have A, B, C on the right. So let me show you with numbers. Here's an example with numbers. 5 plus 1 in parentheses plus 3. And that's equal to 5 plus 1 plus 3. Now notice that my groupings of numbers over here are different. I have 5 plus 1, and then I have 1 plus 3. But if I kind of simplify this down, I have 5 plus 1 is 6, plus 3 is 9. So the left side is equal to 9. And then on the other side, I have 1 plus 3 in parentheses, which is 4, and I'm still adding 5, which is 9. So no matter what, I can change the groupings of the numbers, and my answers on both sides will be equal. But the thing to remember here is that order does not change, like it does in the commutative property. Notice how I still have 5, 1, 3 on the left, and then 5, 1, 3 on the right. So the order of the numbers does not change. Only the groupings change. It also applies for multiplication as well. So some examples for multiplication would look like this. If I had like A times B and then times C. And I can set that equal to A times B times C. And it works the same way as the addition. And here's an example with numbers. I could have something like 2 times 4, and then multiply it by like 7. And then I could say 2 times 4 times 7. And no matter what, each side is still going to be equal to each other. So this is the associative property. Okay, the identity property. The identity property is used under addition and multiplication, very similar to the last two properties we talked about. And what's interesting about the identity property is it stays the same. What I mean by that is I can take any number. For example, I'll take the number A. Remember, variables represent numbers. So if we have A, and if I add 0 to it, well, what am I going to be left with? I'm going to be left with my original A. I like to say that you start with one's identity and you add nothing to it and you have the same identity. It also works the same for multiplication. If I have that same variable A and I'm going to multiply it by 1, I'm still going to end up with my A. So these are my two identity properties under the operation addition and multiplication. My next property is my inverse property. Inverse property, just like the others, is used under addition and multiplication, and I'm using opposites to cancel a value. Remember that the word opposite is just another word for inverse. So these two words, they basically mean the same thing. So I'm looking for numbers that are opposite of one another. For example, if I use that same variable, let's use A, and I add the opposite of A, which is negative A, I'm going to end up with 0. So I'm adding inverses. Now, just like we were saying earlier, not only is this inverse property work under addition, but it also works under multiplication. And it looks a little bit different with multiplication. I'm going to use that same variable A. And if I think about what the inverse of A is, I think about just like a number 4. 4 can also be written as 4 over 1, right? Now, if I flip that over, its reciprocal is going to be 1/4. So similarly, my inverse of A is going to be 1 over A. And that is going to equal 1. All right, the next property is my favorite property. It's the property of 0. The main idea here is that when you multiply by 0, you always get 0. And for example, I could take any number. I'm going to take 17. And I'm going to go ahead and multiply by 0, and it's always going to equal 0. So basically, I can take any number, which I can represent by A, and I can multiply it by 0, and it's always going to give me 0. I can even take a fraction, like negative 1 over, let's say, A, and I can multiply it by 0, and it can give me 0. And the cool thing about this property is I could take a bunch of numbers like 2 times 7 times 4 times 6 times 0. And that big long expression is still just going to be equal to 0. Okay, we talked a little bit about the distributive property in a previous lesson. But basically the distributive property, you're going to multiply a value to an expression inside parentheses. And here's a great example, just using variables. I'm going to say A times B plus C. And if I use the distributive property, remember you don't need to use these little arrows, but I'm just kind of showing you how the distributive property works. We're going to multiply because these parentheses here mean multiply. I'm going to multiply A times B. And if I do that, it's going to give me AB. And I'm also going to take that number that's outside the parentheses and I'm going to distribute it into the C. Now, recognize that it's also a positive C because sometimes it can change and be negative. And that's going to give me a positive AC. Whoops. And that's kind of how the distributive property works. Let me change that number there. Excellent. Okay, let me give you an example with numbers. Let's just use the number, let's put a 2 outside, and we'll say x plus 7. That's a good example. So again, I'm going to multiply 2 times x, and that's going to give me 2x. But when I multiply my number times my number 2 times 7, 2 times positive 7, that's actually going to give me positive 14. Now, where the distributive property gets kind of weird is when you have negatives. Not only a negative outside like this, but when you have a negative like this, like we'll say negative z inside. First, I'm going to multiply my negative 5 times y, and that's going to give me negative 5y. And then I'm going to take that same -5 and I'm going to multiply it by not only z, but -z. And you'll notice that that's going to actually give me a positive number. It's going to give me 5z. That's positive. So this is a really tricky spot with the distributive property, especially with this negative right here. So be very, very careful as you approach problems with that. Okay, we have some more properties here. The first property here I like to call the reflexive property. And I find it to be one of the easiest properties to remember because the main idea of it is that the value always equals itself. What do I mean by that? Well, if I had the variable a, it's just going to equal a. So some more examples of this would be like if you get to the end of a multi-step equation, you could end up with the answer like this: 16 equals 16. That is the reflexive property. And you could also have something like 5x equals 5x. Both sides are identical to each other. And just one more example, just to make it a little bit more complex. Say 4y squared equals 4y squared. So that's the reflexive property. The symmetric property is kind of interesting. Basically what it's saying is if A equals to B, then B equals to A. So I'll show you what I mean here. So if I have this variable A and A is equal to B, well, then what I can say is B is also equal to A. So it's not necessarily the commutative property because I'm not adding or I'm not multiplying. I'm just basically flipping the numbers over. So let me show you an example here. Let's say if x equals 3, then I could also say that 3 is equal to x. That's a pretty basic example. I could also say something like, let's say if 5x was equal to 30, well, then I could also say that 30 is equal to 5x. So basically I just flip-flop them over the equal sign. Okay, the transitive property. This is a cool property. What this is saying is if A equals B and B equals C, then A equals C. Let me go ahead and write that down so we can take a look at it. So if A equals B and then B equals C, then A is equal to C. So for example, let's look over here. Let's look at this example. If, let's say 4 plus 3 is equal to 7, right? 4 plus 3 is 7. And let's say this, and 7 is equal to, I don't know, how about this one? The square root of 49, right? Aren't they equal? Then can't we say that 4 plus 3 is equal to the square root of 49? Think about that for a second. Isn't that true? 4 plus 3 is 7. And 7 equals the square root of 49. So doesn't 4 plus 3 have to equal the square root of 49? Yep. Every time. This last property is called the closure property. And here's what the closure property says. A set is closed under an operation, whether it be addition, subtraction, multiplication, or division, if the operation always produces an element of the same set. If an element outside the set is produced, then the operation is not closed. So here, let me show you through example this closure property. Let's look at the first example here. It says answer true or false. If false, give a counter example. So let's look at number 1. It says integers are closed under multiplication. So what that's saying is I'm looking at the real number system integers. And I'm looking at the operation of multiplication. And I'm saying, okay, well, if I take an integer like, I don't know, 4 and 3, and I multiply them together, isn't that going to give me 12? So I took two integers, I multiplied them, and it gave me a number that is still an integer. So the question is, are integers closed under multiplication? And the answer is yes. So this answer is true. And if you look at that one again, if you're thinking, well, do negative numbers work? Well, try negative. If I said negative 4 times 3, that would also give me negative 12. And remember, negative 12 is also an integer. So no matter what, I'm still going to get an integer. It even applies if I multiply it by 0, because remember, 0 is an integer as well. All right, the next one is natural numbers. Natural numbers, remember, are numbers like 1, 2, 3, 4, and so forth. And they don't include 0 or any of the negative numbers. So I'm looking at natural numbers, and I'm wondering, are they closed under the operation of subtraction? So I'm just going to try, I'm going to try two numbers like this. And I'm going to say 5 minus, 9. And we know that that's going to equal negative 4. And like I said, negative 4 is not a natural number. It's actually a whole number. So, I'm sorry, not a whole number. It's an integer. So it's not a natural number anymore. So, you can see that this is going to be false. It's not going to work. It's not going to work under the natural numbers. How about even numbers? Even numbers, like 2, 4, 6, 8. Are they closed under the operation of addition? Well, I'm just going to pick some numbers. I don't know. Let's do 12 plus 14. And I can add pretty much any even numbers at all, but this is going to be 36. You notice that when I add those two even numbers, I'm going to get another even number. And it doesn't matter what numbers I choose. It's always going to work that way. So this is actually true. Even numbers are closed under the operation of addition. Okay, irrational numbers. Irrational numbers, real common irrational number is pi. So let's talk about pi. So irrational numbers are closed under the operation division. Well, let's just use, pi. Let's make it nice and simple. Let's say pi divided by pi. We can do that, right? Because they're both irrational numbers. They happen to be the same number, but it doesn't really matter. And we know that anything divided by itself is just 1. And isn't 1 an integer? So irrational numbers are not closed under the operation division. And then my last one here, perfect squares. Perfect squares are closed under subtraction. Perfect squares and subtraction. That's what I'm working with. So I know that my perfect squares are numbers like, let's do 25. So we can say 25 and subtract. And we can say 4, that's a nice easy one. And that's going to give me an answer of, let's say, 21. Now, I could look at this and say, okay, well, 25 and 4 are perfect squares, but 21 is definitely not a perfect square. So since it's not a perfect square, it is not closed under this operation of subtraction. All right, that is the end of our lesson on properties today.